Hi everyone, and welcome back to another AP Calculus video. Today we're going to discuss a BC topic called length of curve, and we're going to learn about a formula that's going to help us find the length of a path of some, an object, a point, but basically from one point to another. If it's following along a curve instead of a straight line, we're going to learn a formula that's going to help us find that. And so what we have here is an example of a mathematician who's created a scale drawing of a garden that she wants to enclose in the center between these two curves. And so what we want to do is find the perimeter of this garden so that we can buy fence to put around it. So what we're going to do is we want to basically find the distance from this bottom point up along this blue curve, and then we're going to add it with the distance following the red curve, and they're defined here with these two equations. Now, why these are her favorite equations, we'll never know, but they are, so it's what we have to work with. And what you may notice here is that these two equations are defined differently. One is defined as y equals some function of x, and another one is defined as x equals some function of y. And that's significant because we're going to change our formula based on how the function is defined. So we'll come back to this. Let's take a look at what the formulas are. So here are our length of curve formulas that you want to record down into your notebook. And these formulas you do need to know for your AP exam. So let's talk a little bit about them and how they're different and when you'll use each one. Now, the first one is for the length of a curve that is traced by a function in terms of x. So y equals, or f of x equals, this is the curve, this is the equation that you're going to use for those functions. And most of the time, that's what we have, that's what we're used to. But every now and then we have an equation like our blue equation here on the screen where it's x equals some function of y. And when that's the case, you'll notice that my limits of integration change from c to d. And then they're also defined by dx dy. So this is the derivative of your function. So for every time we use this equation, we're going to have to find the derivative of our function that gives us this line. So we do have to do a little bit of work, but then after that, sometimes we can use our calculator to evaluate the integral, and sometimes we'll have to carry it out by hand. It'll just depend on the nature of the question. But the key here is to understand that when I switch it to dx dy, all that means is whatever the equation is, I'm going to do the derivative like normal. Remember, we have this rule that says whatever the bottom variable is, that's what we're differentiating with respect to. That's what this notation tells us. So when we have an equation in terms of y, so y squared, the derivative is just going to be 2y. So we don't have to do anything special when we find the derivative for this blue equation. We'll just kind of, it's almost like we treat it like it's an x variable, and you'll see that when we have to plug it into our calculator, that's exactly what we're going to do. So let's see how this plays out. Let's go ahead and start by finding each derivative. So I'm going to find the derivative of the red curve. So the red curve is y equals 4 square root of 2 over 3 x to the 3 halves minus 1. So dy dx is going to be 3 halves. So remember, I'm finding the derivative. I know in this chapter, when we start learning about length of curve, we've got integration and differentiation. So we really have to decide what we're doing with our exponents. So don't get confused between the two. That's a really common mistake for calculus students. So 4 square root of 2 over 3 x to the 1 half. So things are going to kind of cancel away. My 3's will reduce. This will reduce to 2. So I end up getting 2 square root of 2 x to the 1 half, which is basically 2 square root of 2x. Well, that's nice. That's dy dx. So now I'm going to find dx dy. So I'll do that over here. Dx dy just means find the derivative. It's just 2y. So I don't have to do anything special. It's not, implicit differentiation where I have to throw a dy dx because it's not an x. Remember, the bottom in that notation tells you which derivative, which variable you're differentiating with respect to. So now I'm ready to plug things in. And I've got two functions here, so I'm going to have to use both variations. Now, let's talk about these limits of integration. You'll notice that for the first one, the limits are a to b. What I want to highlight here is that these are x coordinates. So a and b, these are all x coordinates. So from point A to point B, that's bad. So from point 1 to point 2, a and b refer to the x coordinates. So here, this would be a and this would be b, making d and c my y coordinates. So anytime we have a function in terms of x, all x numbers. x coordinates. If it's in terms of y, everything's a y number. So this would be considered C, and this would be considered D. So we always go left to right or bottom to top. That's how we integrate those. That's how we like our limits to work. So left to right, bottom to top. So we are always increasing in our values. So now we're going to plug them into our equation. So the length of curve for the red curve will be integrated, and these values here that Desmos gives us when I screenshotted it, remember these values probably go more than 4 places. Desmos has some limitations on what it'll display. Anytime you're finding an intersection on your own on the AP exam, it's always good, best practice to make sure that you carry out those decimals to 5 or 6 places. I like to say 6 to be safe, but you're always going to take decimals to 6 places. Now, that's while you're working. And then at the end, when you round to 3 places, you're going to reduce your risk of having round-off error, because the AP exam grades to an accuracy of 3 places, and that's truncated or rounded. So using up to 6 or more is always better. 6 or more within your calculations ensures that you're going to have an accurate answer. So here we go. The red curve is in terms of x, so I'm going to use the x numbers. So 0.3571 all the way up to 1.0483, and I'm going to have the square root of 1 plus, and then I'm going to take that derivative and I'm going to square it. Now this one I probably could have worked out and made it work out so that I could evaluate it by hand, but I'm not going to. I'm actually going to plug it into my calculator. So let's go ahead and pull up our calculator, and I'll show you what it would look like. Now, when I'm plugging things using length of curve into my calculator, one trick that I have is to go to my y equals screen and get everything cleared out. But sometimes I like to just type the derivative into y1. So here the derivative is 2 times the square root of 2x. Now this derivative isn't so bad, but there are going to be derivatives that are complex and have a lot going on. And so doing this trick of typing it into y1 means that when I go back out, when I quit out, and I use Math 9, and I start putting in, all the information for my integral, when I go to type it in to the big square root, there's so much going on. It's so easy to make a mistake, and I have made plenty of them, that one trick that we do is we say the square root of 1 plus, and then if I put the derivative into y1, watch what I can do. I can just say, okay, I'm going to pull up my variables. So there's a couple ways to pull up the y1. You can go to vars, yvars, and it's under function, and there it is, y1. You can choose it that way, or if you hit alpha trace, that F4 function pulls it up pretty quickly. So that's kind of a faster little shortcut there. But you're going to put it in there, and then you're going to make sure that it gets squared. So let me arrow back over, and then squared, and then dx. Now in your calculator, you're always going to use the x variable as your variable. So it'll always be dx. So here we go, enter, and this tells me what my length of curve is there. So 1.765255. And I'm going to more than 3 places because I'm working within my problem. Now I'm going to go over to the other side and do the blue curve and find its length of curve. So this length, I'm going to use the y coordinates on. So I'm going to go from negative 0.598. And again, because it's Desmos, it cut me off. I don't know what those are. If I was finding them in my calculator, I would want to go to 6 places, minimum of 6 places. And then 1.024. And then the square root of 1 plus 2y squared. Now, this is the setup that I would want to show on my AP exam. I'd want to show the derivative. I'd want to show, that I'm plugging it in. And if I use my calculator, this is the minimum that I need to show. So I'm going to plug this into my calculator, much like I did the other one. And here's what it looks like. And remember, on the paper it says y. In my calculator I use x because that's what my calculator understands. And here's the answer that I get. This is the length of the blue curve. following from that bottom point to that top point. So now the perimeter of the garden would be those two values added together. Now, it's helpful sometimes when we don't have color coding to label them L1 and L2, and that way you know, hey, all the ones is the first equation, all the twos is the second equation. When we add them together, this is the work we can show, and our answer is justified. So 4.018 units is the perimeter. Now, this is a scale drawing, so I'm sure the mathematician would scale it up and have some sort of scale factor to know the actual distance in feet or inches or meters or whatever. So this is how the length of curve works, and for the most part we do use our calculator, but every now and then we're going to do one by hand, and so we will see one of those coming up shortly. So let's take a look at a problem like this. So this problem gives us a function in terms of x, so we know we're going to use that second equation, and it says that we want to find the length of curve if x equals this, and we want to go from point, this will be our first point, negative pi over 3 to pi over 4. So the length that I'm going to end up finding looks like this. This is the integral that I need to kind of fill some information into, and I'll have 1 plus, and it'll be dx dy, so the derivative of this equation, and then dy. So this will be, whoops, n squared. This will be my length of curve. So the first thing we need to do is we need to find the derivative of this equation. Now you'll notice it's an integral. And so this is going to bring back and remind us of the fundamental theorem of calculus, part 1. And it says this: when I'm trying to find dx dy by differentiating an integral, and notice this integral has the letter t in it, something other than y, and we're going from a constant, it doesn't matter what constant, all the way to y. When I do this derivative, you can think of it as the derivative and the integral kind of cancel each other out. And whatever this is, we're going to also include the chain rule, right? Because the idea is we plug it in and we would have to treat it as its own function within a function. So if there's, if it's y squared, we would have to multiply by a 2y. That's the chain rule that's involved here. But essentially, the derivative here just turns into the function rewritten with the variable. So I just replace the t with the y. Or if it was a y squared, I'd replace it with y squared and then multiply by the derivative of that upper limit. And so this is my derivative that I'm going to be plugging in. And notice I'm going to be squaring a square root, so it's going to cancel out. It's going to be really nice. So here we go. My length of curve looks like this. So I'm going to have the square root of 1 plus the square root of secant squared y minus 1 squared. That's going to cancel, but this is what I'm going to show, right? And so oftentimes by hand you'll see that square roots and squares will cancel, and we're going to go as far as we can by hand to see what we get. So here we go. So these will cancel, and then I'll have 1 plus the secant squared minus 1. The 1s will cancel, so I'll have the square root of secant squared y. Oh, well, okay. So here is where I'm going to start thinking about plugging it into my calculator. I've got it simplified. The square root of the secant squared is the absolute value of the secant of y, but we're going to worry about that later. I'm actually going to go ahead and plug it in just the way that it is. And I'm going to change the secant to 1 over cosine of y. So it'll be like this, 1 over cosine squared y. And I'm ready to plug it into my calculator. So here's what it looks like in my calculator. And when I plug it in, I'm going to use that x variable, plugging it in, and I get my answer here. Now, I could have square rooted the secant, in thinking about it, 1 over cosine. Negative pi over 3 to pi over 4 is on the right side of the unit circle. The cosine stays positive on that side. So square rooting it would have been just fine here in this case. But when in doubt, stop here and plug it in. Or compare the two results. If you do the square root, you do get the same decimal value, 2.19833. So this is what I would write down, 2.198. And you could also, just as a side note, do this integral, 1 over cosine. You could do the square root and kind of cancel those, and it would be fine. So it's the same. So this is how we're going. This is our length of curve formula and kind of how it works. So we're going to do one last problem, and this one we're going to do completely by hand without the use of a calculator, just to show you that it is doable. Sometimes we're going to get some pretty ugly answers, but it is possible to work these out by hand, and you'll do a few. So here we have an example that we're going to work out by hand. Now this is a pretty complex example, and oftentimes, you know, when you have a complicated derivative, you'll be able to use your calculator, but this is one that we can actually work out to the end, and you'll see that there are some tricks and some things you're going to have to remember to be successful. So let's go ahead and set it up. The first thing we need to do is we need to find dy dx. So with this, the derivative is pretty tricky. So remember, this means 1 minus x squared to the 1/2 power. So I'm going to do 1/2 times the function, but then the chain rule says multiply by a negative 2x. That's the derivative of that inside. So we've got a little bit of simplifying to do. The negative 2 and the 2 will cancel away. This has a power of negative 1/2 that I forgot to put in there that first time. And so the 2 and the negative 2 cancel. I have negative x in the numerator and then the square root of 1 minus x squared in the denominator. So there's my derivative. So now let's start plugging it into our length of curve formula. So we're going to go from 0 to 1, the square root of 1 plus, and now we're going to do this derivative squared. Now, if this was a calculator active problem, this is where I would stop and evaluate using my calculator. And when I do that, using Math 9, I'm going to get this answer, 1.570790754, which should look familiar. It's one of our values from the unit circle. So as you guys are thinking about what that number is, it's a nice number. And I'm going to now work this out by hand. So assuming that I can't use a calculator, and this is not where I would plug it in, here's where I would go next. Oh, and that needs to be squared. So as I keep on moving, I'm going to go ahead and square that derivative. So I'm going to have 0 to 1 plus, the negative x squared just becomes x squared, and the square root in the bottom cancels away. So now what I'm going to do is I'm going to get a common denominator. I'm going to combine everything up. So I'm going to make this 1 minus x squared over 1 minus x squared. It's a form of 1. And when I do that, I can kind of combine everything here. It becomes 1 minus x squared plus x squared. Those are going to cancel away, all over 1 minus x squared dx. Now as I keep on moving through, this numerator turns into 1 over 1 minus x squared. Now this looks familiar to me, and if I square root the numerator and the denominator separately, the square root of 1 is just 1. I get 1 over the square root of 1 minus x squared. Now this should look familiar because it's on one of our formula sheets, and there are two inverse trig functions that I said we need to be familiar with, tan inverse and sine inverse. And this is the derivative of sine inverse. So if you guys don't remember that, when I do d dx of sine inverse of x, it's simply 1 over 1 minus x squared square rooted. Now if there's a function of x in there, then you have to do the chain rule, of course. But this is the derivative of sine inverse. And so when I integrate it, this integral becomes sine inverse of x, and we're going to evaluate that from 0 to 1. Well, that's just sine inverse of 1 minus sine inverse of 0. So which angle has a sine of 1? Pi over 2. Which angle has a sine of 0? So your answer is pi over 2, which consequently is 1.570790754. So it is possible to work these out by hand and to find the lengths of curve using antiderivatives and simplifying and things like that. It does get tricky, and the algebra is what is going to hold us back really on being successful on problems like these. But you can work them out, you can find it, you can do it. It just takes a little bit of work, a little bit of studying, and a little bit of just remembering some things that maybe aren't quite at the front of your mind. But no matter what, keep at it, you can do it, you can be successful.